All right, let's continue. So our next speaker is Hussein Ben Dali and is going to tell us about the proof of Lassalle's conjecture.
Thank you very much, and thank you for all the organizers for this great conference. So I am going to talk about joint work with Maciej Doinga from the Polish Academy of Science, and in which we have obtained the combinatorial interpretation of the Jack characters in terms of non-oriented maps that we have used to prove a positivity conjecture of Lassalle. So let me start with some definitions related to symmetric functions. So I will consider symmetric functions in infinitely many variables xi's. And so this is the space of symmetric functions. It has many nice bases, all indexed by integer partitions. And in this talk, I will be considering power sum symmetric functions as a basis of this space. So these power sum symmetric functions are defined as follows. So first, we define them on integers. So if we have a positive integer k, so pk is the sum of all the xi to the power k. And then we extend this definition by multiplicativity to partitions. So p lambda would be the product of the p lambda i's. So now, when we look at the expansion of Schur functions on the power sum basis, so if you look at the expansion of Schur function S lambda on the power sum basis, the coefficients which appear are directly related to the characters of the symmetric group, chi lambda, up to some normalization factor. So Jack polynomials are also a basis of the space of symmetric functions. So they are indexed by integer partitions, but they also depend on one deformation parameter alpha. So the exact definition of Jack polynomials won't be necessary for this talk, but they can be obtained as a limit of Macdonald polynomials. And more importantly for this talk is that they deform Schur functions. More precisely, when we take alpha equals 1, we obtain Schur functions. And the main result I'm presenting today is that we give a combinatorial interpretation of the expansion of Jack polynomials in the power sum basis. And this combinatorial interpretation is in terms of bipartite maps, which are oriented or not. And I will explain this in the next slide. So actually, there is so the coefficient we are looking, so since the expansion of Schur functions in the power sum basis are given by the characters of symmetric group, the coefficients we are considering here are a natural one-parameter deformation of the characters, reducible characters of the symmetric group. And actually, there is another combinatorial interpretation of these coefficients given by Wilson and Haglund, which is in another direction related to tableau and attacking graphs. So before telling you what is a non-oriented map, I will start by some motivations of why we are trying to connect Jack polynomials to non-oriented maps. So first, this is a generalized known combinatorial interpretation of Schur functions, which is in terms of a particular family of bipartite maps which are oriented. So originally, this combinatorial interpretation has been given in terms of permutations, but there is a nice encoding of maps with permutations. And then we also use this combinatorial interpretation to have a positivity conjecture, to give a proof of a positivity conjecture of Lassalle related to Jack characters. And I will explain this conjecture by the end of my talk if I have some time. And this also answers, in some sense, a conjecture of Hanlon from 88, but I won't go into the details of this conjecture. So maps were introduced this morning by Eric and Wenji, but there are some differences in the definition, so I will start by introducing these objects. So in this talk, I will be considering maps which are oriented or not. So first, a connected map is a connected graph which is embedded into a surface, and the surface can be oriented or not. So in particular, we are considering surfaces of higher genus, but also they can be non-oriented. And more generally, a map is a collection of connected maps. So for me, a map can be connected or not. This is for this talk. And we will say that a map is oriented if all the connected components are embedded into orientable surfaces. And all the maps that will appear today in this talk are bipartite, which means that vertices have two colors, white and black, and each edge connects two vertices of different colors. So we have here an example of an oriented bipartite map on the client bottle. So the square here represents the client bottle. So the sides should be glued using following the arrows here. And the graph inside represents the map. So when we have a map, we can associate, it has faces, so we can associate to it a partition called the face type of the map, which is obtained as follows. So we look at the degrees of all the faces, but here we have bipartite maps, so all the faces have even degree. So we can look at the degrees and divide by 2, and then by reordering these degrees, we obtain the face type of the map, which will be denoted with a diamond in this talk. So for example, here we have a map whose faces have degrees 8, 8, 4, and 4. So the corresponding face type would be 4, 4, 2, 2. So, so the generating series will consider of maps which are bipartite, oriented or not, connected or not, but they also have an extra structure that we call the layered structure of the map. And this layered structure works as follows. So we fix a positive integer k, and we say that the map is k layered if each one of the black vertices has a label, integer label between 1 and k. And once we have fixed a labeling for black vertices, this defines a labeling for white vertices, which is defined as follows. So for each white vertices, we look at its neighbors, and we pick the maximal label. So for example, here we have a white vertex that has 3 black vertices of labels 1, 1, and 2. So it will have the label 2. So this is an example of 3 layered maps because all labels are between 1 and 3. And we don't add any condition on these labels. So this definition appears in previous works, but under different formulations. So now we have all the combinatorial objects that will appear in the generating series, but now we should understand how this is connected to the alpha parameter of Jack polynomials. So how they are related to these non-orientable maps. So to do so, we use this definition of Goulden and Jackson that they introduced in the context of the B conjecture, which is another conjecture related maps to Jack polynomials, which is still open. So we say that a statistic so we call a statistic of non-orientability on maps, and for us on k-layered maps, is a statistic which associates to each map a non-negative integer such that this integer theta of m is 0 if and only if the map is oriented. And in all the generating series, we will be counting maps with a non-orientability weight, which is of the form b to the power this statistic of non-orientability. And b is the shifted Jack parameter given by alpha minus 1. So this shift has been introduced also by Goulden and Jackson. They observed that when we realize this shift, we obtain a nice positivity results. So the reason we are doing that is that the situation is the following. Usually we have generating series of oriented maps, and we have generating series of all maps, oriented or not. And we want to look at some generating series which interpolates between both of them. So by taking these non-orientability weights, we can do so because now when we take b equals 0, or equivalency alpha equals 1, only maps with the statistic 0 will appear in the generating series. And these maps are exactly orientable maps. But now when we take b equals 1, we will recover the generating series of all maps without any weights. So it was the trick of Goulden and Jackson to introduce some interpolation generating series of maps, which is a non-orientability generating series. And actually this definition is not very enlightening because it does not give any restriction on these statistics. But intuitively in practice, we tend to think of these statistics as some measure which quantifies to what extent a map is orientable or not. And this is, in general, it's hard to find a statistic that works. So our result says that we can find an explicit statistic of non-orientability theta, such that a Jack polynomial j lambda can be written as a sum over bipartite maps, oriented or not, which are layered and they have number of parts of lambda layers. So here we have, there are many normalization factors, but the most important thing in this formula, there are 3 weights. So the first weight is a face weight, which associates to each map a power sum function indexed by the face type of the map. And the second weight is this non-orientability map, which is given by this statistic of non-orientability. And the third weight is a weight which is related to the structure of layers of the map. So this third weight associates to each white vertex, which is labeled by I, the weight minus alpha lambda I, where lambda I is the part number I in the partition lambda. Yeah, of course.
So of these three things at the bottom, the face weight, etc., how many of these see the symmetric variables, and how many of them are not depending on like the variables?
So your question is what weights do not depend on the variables? So which variables do we mean?
Well, because the Jack function is a symmetric function in variables x1 through whatever.
Yeah. So okay. So the variables xi, the underlying variables, they only appear in this power sum function.
So,
exactly. So because the power sum function is it encodes all the variables that are behind, and all the other weights are just And yeah, that's a good question because the variables, the xi variables are here in this face weight, and the dependence on the parts of the partition lambda are just on the third weight. So it's somehow decorrelating these two types of dependency on variables and the partition indexing the Jack polynomials. And actually what we prove is something more general than this, is related to Jack characters, which have been introduced by Lassalle. So a Jack character indexed by mu is a function on Young diagrams, which is defined as follows. So when we evaluate this function on Young diagram on a partition lambda of size smaller than the size of mu, it gives 0. And if the size of lambda is bigger than the size of mu, so what we do is that we start by completing the partition mu with parts of size 1. So that's we have two partitions of the same size. And then we look at the coefficient of the power sum function p mu 1, 1, 1, 1 in the Jack polynomial j lambda. And then we add some factor. So the most important thing is that when we look at two partitions of the same size, we get exactly the coefficient of p mu in j lambda. And we prove that there exists a statistic of non-relatability such that this Jack character has also a nice combinatorial interpretation in terms of maps, except that here we are looking just at partition mu, so they have exactly face type mu, and then we have the same kind of weights on the right. So the non-relatability weight and this layers structure weight. And actually this result has been known for two values of alpha, alpha equals 1, alpha equals 2, which corresponds to the characters of symmetric group and the characters of the zonal characters, which are obtained from the zonal polynomials. And the first formula for alpha equals 1 is known as the Stanley-Ferré formula because it has been conjectured by Stanley and proved by Ferré. And the second one has been also proved by Ferré and Schniade. The only problem is that these two proofs, they use representation theory tools. So for the first one, we use the representation theory of the symmetric group, and the second one is the representation theory of a Gelfand pair. But there is no interpolation of this representation theory tool. So for general alpha, we don't know how to do representation theory for Jack polynomials, so we should use different techniques. And the idea is, instead of thinking of these Jack characters as functions on Young diagram, we think of them as shifted symmetric function. So we say that if f is a function which depends on an alphabet of variables ui's, we say that is alpha shifted symmetric if it is not symmetric not in the variables ui's, but symmetric in ui's minus I over alpha. And there is this nice fact, which is, I think, it's a consequence of the work of Knopp and Sahi on shifted Jack polynomials, which says that there exists a unique alpha-shifted symmetric function f mu for each mu, which realizes the Jack character, such that which means that when we take the Jack character theta mu and we evaluate it in lambda, this is exactly equivalent to evaluating the shifted symmetric functions in the parts of lambda. So from now on, we will be thinking of these Jack characters as shifted symmetric functions. And then we have this nice characterization theorem of Ferré, which tells us that the Jack character can be characterized by three conditions. So first, it's an alpha-shifted symmetric function of degree the size of mu. And then we have a condition on the top homogeneous part of this function. So it's given by the power sum function p mu up to some normalization factor. And then we have the third property, which is a vanishing property, which says that when we evaluate this Jack character on partitions lambda of small size, we get 0. And these fully characterized Jack characters. So from now on, we can completely forget, so we don't even need the definition of a Jack polynomial, and we can try to prove that the generating series of these layered maps, they satisfy these 3 conditions. So what we do is that we introduce, for each k, the generating series of k layered maps, and we want to prove that by induction that this satisfies these 3 conditions, but it remains these important questions: what statistic of non-mutability to consider here? And it turns out that the right, because many statistics have been tested and failed, and it turns out that the good family of statistics of non-mutability are the statistics for which we can write differential equations. More precisely, we prove that for some statistics, we can obtain the generating series of k layered maps from the generating series of k minus 1 layered maps by applying some differential operators. And in terms of maps, this corresponds to some Tott decomposition, which states that we can obtain a k layered maps from k minus 1 layered maps by adding edges. Yeah. Yeah, the SIs are they are generic parameters, and at the end we will substitute these SIs to lambda i's. But in this formula, the SIs are generic parameters. Thank you. And so the idea is that these operators at the end they have some definitions using some operators which have been introduced by Chapuis and Doenga in the context of their work on the big conjecture. And the definition, they use some catalytic variables, an alphabet of catalytic variables, Y, which is kind of usual tools in the in decompositions. And what we do is that we, in order to prove that this generating series of layered maps satisfy the conditions of the characterization theorem of Ferré, we should understand how these operators Bn, which construct maps, how they commute between each other. And this is actually a technical part because in the definition of each one of the Bn's, we have one catalytic alphabet of variables. So when we take 2 Bn's, so we have 2 catalytic variables y and z, and the definition and the proof are a little bit technical. So I will conclude with some applications of this result. So first, we can deduce from the proof that we have new constructions of Jack polynomials by creation operators that I denote here Bn plus, which are defined with these Bn operators of maps. And these operators, they allow to obtain a Jack polynomial by adding the rows of lambda 1 by 1. So we start by applying B lambda L and so on until B lambda 1. A more important consequence is this Lassalle's conjecture from 2008, which is related to multi-rectangular coordinates of the partition, or sometimes called Stanley's coordinates, which is, so when you take a partition, we can decompose it into rectangles, not in a unique way, but if we have 2 sequences of integers s and r, such that s is decreasing, we can associate to it a partition in this way. So now, instead of thinking of these Jack characters as polynomials in the parts of the partition, we think of it as a polynomial in these coordinates. And what Lassalle's conjecture says is that when we do this and we normalize correctly, so this polynomial is actually positive in the ri's and the minus si's and the deformation parameter b of Jack polynomials. So I told you that we use this combinatorial interpretation in terms of maps to get Lassalle's conjecture, which is not completely precise, because using this formula we get the non-negativity of in the conjecture of Lassalle. And as you might have noticed, that there are some normalization factors in the formula, so we don't have integrality. And to obtain integrality, we use a completely different approach, which use a family of operators which diagonalize Jack polynomials and which are related to an integrable system of Nazarov-Skilianin. And there is also a nice combinatorics behind related to Lukashevich paths. But I won't tell more details about this. Stop here. Thank you.
All right, any questions? Yes.
So, for alpha equals 1, does your combinatorics somehow naturally recover like a Merkheim-Nakayama rule?
So the question was, is the combinatorial interpretation in terms of maps recover the Morgan-Nakayama rule? So I think that these are kind of two different directions. So for symmetric functions, for sure functions, for example, so for the character of the symmetric group, there are Morgan-Nakayama rule, but there are also this combinatorial interpretation of maps, and I am not aware of any way to connect the two of them. Yes?
So your creation operators, they must be closely related to vertex operators for sure functions.
So the question was, are these correlation operators related to the vertex operators? So I know that for sure functions there are this kind of formula, but I think that our formula is, when we take alpha equals 1 in this formula, we do not recover this formula for sure functions. I think so, because so when you take alpha equals 1, there is already, we obtain sure functions, but with multiplied by the product of the hook. So it's not exactly the same normalization. And I think I was trying to look at this, and I think it's not exactly the same formula at alpha equals 1.
In that case, are there different annihilation operators that are linear algebraic adjoint to these, like in vertex operators?
Can you repeat, please?
Is there an annihilation version of the operator? You have creation operators. Are there annihilation operators?
So are there annihilation operators? We did not look at this direction, but we can discuss this. Yes, so we think that thank you. So the question was, are these operators related to operators on Macdonald polynomials? So I think it turns out that these operators in the language of Macdonald polynomials are kind of theta operators for some families of symmetric functions. And so it seems to have some connections with the Macdonald operators. Non-relatability.
You said it's some explicit thing.
Yeah, thank you for the question. So the question is, how do we define this statistic of non-relatability theta? So the idea is that we are using these third decomposition ideas that we take a map and we decompose it by deleting edges in some algorithm, and this algorithm differs from one paper to another. And then the idea is that for each edge that we delete, we have two choices, either to decide that this edge is contributing to the non-relatability of the map or not. So if we think that in some sense it is contributing to the non-relatability of the map, we decide that statistic should increase by 1 by adding this edge. Otherwise, it doesn't change. Yeah.
I can finish with a question. So your Jack interpolation polynomials, are they related to the Knop-Psi interpolation polynomials for Macdonald polynomials? Because they also are defined in terms of vanishing conditions.
So yes, so I think that so there is this okay. The question is so there is this Lassalle's isomorphism which goes from the world of symmetric functions to the world of shifted symmetric function, and so this isomorphism sends the Jack polynomials to the shifted Jack polynomials, and it sends the power sum functions into the Jack characters. I don't know if this answered your question.
I'm not sure that answers my question. I'm just trying to understand how this shifted Jack polynomial, which seems to be an interpolation polynomial because it's defined by vanishing conditions, relates to similar such polynomials in the Macdonald setting that were defined by Knopf and Psi and later also Kunkov.
So the way I see it as an interpolation is that there is this alpha parameter, so the condition of alpha shifted symmetric here. So there is an alpha here, so that when we take alpha equals 1, we have the correct characters of symmetric group, and when we have alpha equals 2, we have, for example, the zonal characters, and in this sense, it interpolates between the two of them. But I am not sure
okay.
that...
We can discuss it later.
Okay,
all right, let's thank the speaker again.